like last speaker in this session is Professor Andrew Bernevig from Princeton University, and he was talking. Okay, sorry.
Okay, thank you so much. Thanks so much for having me here. I obviously don't have the amazingly funny stories with Allan that a lot of other speakers have, but you know, obviously I heard about Allan through the GMP story when I was an undergrad, and then through some friendly competition with Su Sheng's group with the spin Hall effect with Allan, Jairo, and Thomas and other people. But going back through my email to try to find some compromising photos, which I don't have, I realized that I kept asking Allan for stuff since since 2005. For example, postdoc recommendations. If this works, that was going to be an okay joke, but if it's not working, it's not okay. So postdoc recommendations, loan letter. Can you write this for me? Can you do this? Can you please? Which to all of them, Allan replied obviously very graciously. He was always said yes. But then, it does explain some of the more recent delays in replying messages. Nobody wants to hear just requests for things. And then when, my first interaction with Allan, not at a, sort of student or postdoc to professor level, where we were both, I was a professor in Bogota. And, this was, I think, 2013. And that was the first time we went for drinks out, and we started talking some physics. And for people that know me, they know I can hold my liquor. But especially something with the air in Bogota meant that I got a little bit confused about the physics we were talking about. And then I went back to the hotel. I went back from the summer school back to Princeton, and I hoped that the conversation would be forgotten because I had nothing good to add in the physics that Allan was talking about. But then I received an email from Allan. I promised to get back to you to calculations we've been talking. The email has 2 pages, and you don't want to see the rambling response that I gave to that email. So basically, after several other science discussions, and this is Science Magazine because of the Majorana work with Ali, several papers on Majorana and TBG, and after working on BM models and also more recently on MacDonald models for the past 5 years, I have to say what an honor and a privilege to be here. So happy birthday again, 3 years late, but now I'll get to the title of the talk. So basically the title is how Allan made 10,000 p orbitals be equal to 1 F electron. And I'll try to, for people that have heard this many times before, to try to bring some new results in this talk. So the people that have done this work are the first 3 people here, the work that I've been talking about. But of course, we have amazing experimental collaborations with the Efetov group, Ali's group, Emmanuel's group, and more recently with Eva, Stefan, and Frank Coppens. And I benefited especially from many conversations and papers with these 4 young authors and these multitude of senior collaborators, which I thank them very much. So basically, you've heard this in many talks, including Pablo's talk this morning and Rafi's talk. This is the celebrated Bistritzer-MacDonald model, where you have bands from -4 electrons to 4 electrons. 0 is going to be charge neutrality. And there's a quantum number, which is spin. There's another quantum number, which is valley. So there's 2 bands per valley per spin. They're, of course, a metal in non-interacting physics. But then when you add interactions, or i.e. the real world, this is how the phase diagram looks. And, this is from Efetov's group, but of course, the superconductivity developed in the sample started with Pablo's discovery. And here, I obviously have to say that Eva's inspirational work on flat bands before any theorist was thinking about it basically made the field start. And of course, the work by Emmanuel, Philip, Ali, Andrea, and other people groups, which I'll go through the talk here. Now, what we're trying to sort of understand here is the nature of both these correlated insulators. I won't have very much to say about superconductivity just because I think we cannot predict, well, you know, we can predict some things as you'll see, but I still don't know if it's electron phonon or electron-electron interactions. But what we'll try to understand is the nature of correlated states and the state, the symmetric state above any ordering temperature, which is also interesting. And the basics of every such endeavor is just the Bicester-MacDonald Hamiltonian. And this is kind of a remarkably beautiful model that, as I'll show, contains many different aspects of physics. In particular, I'll show that at the magic angle, the interacting physics is that equivalent to a new topological fermion system where 10,000 of these p orbitals, pz orbitals of graphene on the Moiré scale have just become one px plus minus ipy symmetry F-type heavy orbital. So, as this is not how we came about to this unitary transformation of the BM model, but really in hindsight there was a lot of experimental evidence for the fact that you should have local moments in this problem. For example, you can see the STM results of Ali, Eva, and Stefan, many people, which Allan pointed out that can be interpreted as some Hubbard U-type physics on these AA sites where the charge density resides. This actually is already in the in Rafi and Allan's paper, this localization of charge of these bands on this triangular lattice. And then there's of course local moment physics seen by early on by, and now by other people, by Shahal and Andreas groups. But of course, there's all this delocalized physics from Pablo, Phillips, Eva Ali, Efetov, and many other groups where you can see, superconductors, Chern insulators, metallicity, etc. So in the abstract of Shahal's paper, there's this statement which says that the correlated state features seemingly contradictory properties, some associated with itinerant electrons and others associated with localized moments. So if you take this to face value, you have to ask, well, the BM model has flat bands. Can I describe them in terms of localized electrons? And it becomes pretty clear very fast that that's impossible. And the impossibility of this is because these bands are topological. So without breaking symmetries, you cannot describe them as localized, exponentially localized Wannier orbitals. Now, the issue in these bands is you can then ask where exactly is the problem, is the obstruction to representing them as localized orbitals. And very fast, you find out that the obstruction is at the gamma point. In fact, these representations at the gamma point, which here just means some crystallographic lingo, are incompatible with that of an atomic localized state, such as would be flat bands with no hopping between them. But these other representations at the M and K point are compatible. There's no Wannier orbitals, but what you can see immediately is that if you look in an energy window where the Hubbard interaction is active, you estimate Hubbard interaction 30 to 50 milli-electron volts. If you look in this Bicester-MacDonald model in an energy window where this Hubbard interaction is active, you can immediately see that there are bands with representations that could be swapped for these gamma representations for these ones of the flat bands to actually form an atomic limit. And you ask, well, what would two bands that have this representation at the K point, this at the M point, and gamma 3 at the gamma point look like? Well, you could make very localized orbitals that have this symmetry, px plus minus ipy, two of them per valley per spin, that sit at the triangular lattice. And they look exactly like, the STM images or like Rafi and Allan's picture of the density of charge in these bands. They're actually localized at the AA site of the Moiré lattice. They're formed out of thousands, 10,000 PZ orbitals of the original graphene. So they're actually an effective orbital. And then you can ask how much of the Bicester-MacDonald bands do these orbitals make up? And you take a projection. There's an automatic method by Wannierization in this energy window and then projection that you can ask this question and get an answer to it. And you find out that 95% of the flat bands are made out of these very localized electrons. And of course, the flat bands at the gamma point have zero overlap with these electrons because they're a different representation than these F electrons. These F electrons, which I'm calling them F electrons by abuse of language, have this two-dimensional representation, and nothing at the gamma point has no such two-dimensional representation in the Bicester-MacDonald model. So the flat bands of the Bicester-MacDonald model have zero overlap with the F electrons around the gamma point, but everywhere else, it's almost 100%. So of course, you can't just represent the Bicester-MacDonald bands as just purely F electrons, because there's portions where they get zero overlap. So then you ask, well, what can we represent them as? And you can form the projector into 1 minus the F electrons, then project the Bicester-MacDonald Hamiltonian onto that subspace, and you find out, you can also derive it by symmetry, but you can just work it out. And you find out that the remaining electrons are that of untwisted AB bilayer graphene, with this gap here between these two one-dimensional representation being exactly the Bicester-MacDonald bandwidth at the gamma point. And there's a double vortex here at the gamma point, which actually picks up the topology of the bands. The bands were topological in the Bicester-MacDonald. These flat bands here, the red, are just the F electrons, because their localization is 0.2 of the Moire-Briand zone. Their Hamiltonian is 0. There's no direct hopping. This is their Hamiltonian, 0 here. And then there's another four-dimensional fermion with a double vortex at the gamma point, which picks up the rest of the representations at the gamma point in this energy window and the topology, whose Hamiltonian is this. If you just go and diagonalize this Hamiltonian, it's exactly the Hamiltonian of bilayer untwisted graphene. So then you ask, well, you know, this band structure like this looks nothing like this with a two flat bands and a double vortex. Well, that's because I haven't coupled them, and the coupling also comes from the Bicester-MacDonald model. You can just take a projector into the light electrons, Bicester-MacDonald model project into the heavy electrons, and find the coupling. And of course, it's a constant to first order because the representations of the F fermions and that of the double vortex are the same representation. So it's a constant. So if you take this Hamiltonian plus some plane waves, this Hamiltonian with a constant where the F electrons coupled to the C electrons, to the light electrons, so we'll call them F and C, you get this match between the Bicester-MacDonald model, black lines, and this heavy fermion model, red lines. I'm actually not sure if black and red are Bicester-MacDonald and heavy fermion or vice versa, but it doesn't matter. This gamma here is actually just the gap between the first band and the flat bands here, and this M is just the bandwidth of the Bicester-MacDonald model. Okay, so far is just a unitary transformation of the low energy degrees of freedom. Is this useful? Well, because the F electrons are so localized, you expect them to carry most of the interaction. And indeed, you can take the Coulomb interaction and they can project it to this F and C electron space. And then you get the largest interaction in the problem is this Hubbard-U interaction between the F electrons. You get some other interactions which are not really just, this isn't the classical Anderson model, it's Anderson-like model, but you get some other interactions, which is density interaction. This W is a little bit smaller than U. There's a density interaction between the F and the C's, but this you can treat in mean field. Then you get some other interaction, which is essential for ordering, for the order states, which is a ferromagnetic coupling between some large spin of the F electrons, some large spin of the C electrons, and some Coulomb of the C electrons. The Coulomb of the C electrons, since they're they have a large velocity and they're gapless. This one you can treat in mean field. You can basically treat everything in mean field except for these correlations U. So now we're at the state where all the correlations are in the F electrons, and they have zero kinetic energy, strong correlation effect, and the C electrons are itinerant and are weakly correlated. So you ask, well, can we make more progress? It's not very clear that you can because Anderson models are very complicated, but certainly in one limit, the limit where you don't have zero hybridization between the F and the C electrons, i.e. where this gamma term was 0, you can make a lot of progress because the model becomes exactly solvable. Now, it's unclear if this is the correct limit, but the model becomes exactly solvable there, and you have the filling of the F and that of the C's be independently good quantum numbers. So let's look at this model. What happens, remember, there's zero hybridization. So you see the F's don't couple to the C's. Remember that the Fs in the Bistritz and MacDonald non-interacting model were here at zero energy, but now they've moved to upper and lower Hubbard bands because of the Hubbard U. So these are the F Hubbard bands. The state is still symmetric. These are Hubbard bands here. And now I'm at half at charge neutrality. I'm sitting here. So now we try to basically move from charge neutrality and dope the system. Let's try to dope it at negative doping. It's obvious that the first thing that I'm going to dope in this zero hybridization model is this C electron. So the filling of the C will grow and the filling of the F electron stays constant because I'm just doping here. So the filling around the integer fillings is controlled, the physics around the integer filling is controlled by the F electrons, whose filling stays constant. At some point, my Fermi level will reach here at the lower Hubbard band, where it becomes unfavorable to further continue down and fill up the C electrons. And then what will happen is that there will be F electron transferred here. As you can see, the filling of the F electron goes from 0 to -1, okay? And a subsequent jump in the C electron filling to take into account the change in density. So these are the cascades of transitions that are seen in experiments. And these cascades of transitions basically give you different physics. One of them, which is a local moment physics, which are around charge neutrality and integer fillings, and the other one, which is a mixed valence region of fluctuations between the F and the C electrons. So let's analyze each of these separately. At integer fillings, what we like to claim is that you can have symmetry breaking. It's not clear that you do in all the models, but you can have integer. You can in some models. So in this Hartree-Fock calculations, and I stress that these Hartree-Fock calculations in this heavy fermion model are the same as the Hartree-Fock calculation that you do with the Bistritz and MacDonald model in momentum space. It's just they done different bases. I'll tell you what the difference comes from Hartree-Fock in momentum space later. But in this integer filling where you can have symmetry breaking, for example, what you have at half filling, you have this picture with the Hubbard bands, but now you start increasing the hybridization between the F and the C electrons, and these points, these degeneracy points, will now split because you have avoided crossing, and the band structure will look like this. This is zero strain. We'll get to non-zero strain later if I have time. But the band structure starts looking like this. At non-integer non-zero filling, so filling 1, what happens is there's a Hartree shift because of that W term, the density term between the F and the C electrons. Remember, the filling 1, 2, 3, 0 is fixed by the F electrons. They have integer filling. But if you're away from filling 0, you're going to have this charge term between the F and C electrons, which shifts these relative Dirac cone with respect to the Hubbard bands. And then after adding hybridization to open these band crossings, you get an asymmetry between 1 plus epsilon filling and 1 minus epsilon filling. And this is a light heavy asymmetry that's also seen by a lot of other works in Hartree-Fock in these models. Now, how do we see this light heavy asymmetry? Well, some people say that we can see it in Landau levels. They're certainly consistent with that, but there's other explanation for Landau levels. But one experiment that I like to quote for this is Dima's experiment with the split gate, is about thermoelectric response. Now look what's happening around 0. You have the Seebeck coefficient is particle hole symmetric, but we're going to concentrate here on filling 1, where he sees an insulator. The same thing happens at filling 2 here. But basically what you see at filling 1 is that even though you have holes and electrons across a correlated insulator, same thing happens at filling 2, what you see is that the Seebeck coefficient doesn't change sign as it should for electrons and holes. For electrons it should be negative, for holes should be positive. Now, you can do DMFT or IPT and get some results, but I like to show a kind of, the physical picture of why this happens. Now, the physical picture is the following. If I just had mass asymmetry, I told you that there is a mass asymmetry heavy to light, light at 1 plus epsilon, heavy at 1 minus epsilon. then you'll still see, if I have an insulator, you'll still see a peak. It will still see a peak, a positive peak in the whole doping around 1, except this peak is going to be very different from the one at electron doping, which is going to be asymmetric due to the asymmetry of masses. It's not going to be totally negative as it is in the experiment. But now, for a heavy light electron where most of this heavy band is actually localized, so actually does not have any scattering, you also have an asymmetry in times, and this comes out of the DMFT, that the scattering time for these electrons is much, much larger than the scattering time for these heavy electrons. These are the light electrons for these heavy electrons, and this suppresses this peak to negative. Of course, if you go to very low temperatures, you're going to still get a positive peak, but in these Seebeck experiments, they can never go to super low temperature because they're shining light on it. So just a very simplified model with both mass and lifetime asymmetry can explain this. Now let's go to the symmetric state. So those were the symmetry broken states. Now I want to go to the symmetric state. And if there's one thing to get from this picture is the spectral function. Pablo this morning said that, there's experiments, I think he quoted Shahal's group, there's very interesting experiments. Well, there's certainly colloquiums around the web that you can look at. I won't say what the result is, but I would like you to look at the spectral function and keep it in mind as the spectral function is calculated. Now, the spectral function is just a different color coding of this DMFT spectral function on the left, okay? And it was obtained by several authors, including Valenti, Sangiovanni, and Welling, and Bascones. It's gapless at the gamma point, but it's got flat bands everywhere else, and there's a large, around 35 to 40 electron volts gap between these Hubbard bands, and then at the gamma point, it becomes dispersive and gapless. And this is just the heavy and light electrons. And so this is how it should look, the spectral function measuring QTM at low temperatures, but above the ordering temperature. Then you can ask, what happens to the Kondo physics? Is there Kondo physics in this model? Well, if I'm sit at 0 filling, okay, i.e. in this spectral function, the density of states here is probably small enough that you won't see Kondo peaks. But I can move to non-integer fillings where the density of states is larger. And what you see, for example, at filling 2.3, what you see is, first of all, you see some C electrons density. You see some Hubbard bands. There's a Hubbard band here, but it's very diffuse, so you can't see it. But as you lower the temperature, you can see the Kondo peak developing at the Fermi level. Now, why am I bringing this Kondo peak? You can do more serious DMFT, which is what the group of Valenti, Welling, Sangiovanni, and Antoine Georges did with Gautam Ray and Lorenzo Kripa. But basically what they did is they showed that there's a very different behavior in susceptibility when you're at integer fillings. Don't trust the fully very low temperature. Integer fillings versus non-integer fillings. Integer fillings looks like local moments. Non-integer fillings could have Kondo physics. Now, the reason why I'm bringing this up is because of the first set of experiments in STM. And these set of experiments at the beginning were interpreted as these cascades being Hubbard bands. I think Pablo showed today a similar Hubbard band cascade, although he didn't call it Hubbard bands. Now, these were interpreted at the beginning as Hubbard bands, but you can see that there's an extra thing in these experiments, which is this peak that at some point sticks to the Fermi level. There's strain in these experiments, which has to do with the gap here, but there's a peak that starts getting close to the Fermi level that could be a putative Kondo peak. Now let's look at the new set of experiments, which I got permission from Stefan groups to show. This is on tri-layers, but tri-layers should be similar to bilayers with the exception of the large Dirac fermion, which doesn't really couple very much. It can influence some of the filling, but what I wanted to point out is the line cuts versus temperature. Okay, and you can see that at low temperature, there's line cuts with a bias peak exactly at 0. And as you increase the temperature, there's two phenomena. The bias at some point depins off of 0 and starts moving up, exactly like the Kondo peak that I showed before. And then you can see that the broadening is very different from the thermal broadening. Thermal broadening is the dashed lines, the broadening is much faster than the thermal broadening, which is also expected in a Kondo regime. In fact, this is the DMFT result for the tri-layer, and you can clearly see Hubbard bands. You can clearly see the peak pinned to the Fermi level until some temperature where it starts deviating from the Fermi level. And I can assure you, I had another slide here. It's completely different from the thermal broadening, which would respect the peak. Now, the only issue is the energy scales don't fully match. These temperatures are lower by a factor of about 3 then, or 2 than the actual ones in DMFT. But I would say that everything else can be explained. Now, superconductivity, I'm going to go fast. But this one, I'm not, you know, I'm not going to sit and admit that we match superconductivity. If you do just electron-electron interactions in the Kondo state, which screens the large Hubbard Q on site, you get the nearest neighbor attractive interaction, which is this. This gives you triplet superconductivity that's also gapless. So it would match the experiment, but in fact, you can get similar things with electron-phonon coupling and with other methods. So I think, you know, effort to converge on what the mechanism of superconductivity is obviously needed. But at least I would say that the Kondo lattice and the Fermi liquid at low temperatures allows you to get a mechanism for screening the large Coulomb interaction that's valid over a large filling range and not just at some Van Hove singularities. Now, the symmetric state of TBG, I quoted our results, but of course, there's many other people who had similar results. These are some of the results in the literature. For example, you can see Bascones DMFT spectrum looks very similar, and there's many other results by all the people here that are very similar to this that I urge you to take a look at. Now, in the last 3 minutes, I will try to tell you something about strain. So strain adds a different perspective, as you know, Ali and Stefan's experiments showed, to the situation. And this perspective can be incorporated in the same formalism by really taking the Bister-McDonald Hamiltonian, adding strain to it, and doing a continuum model. This is like basically Bister-McDonald plus other terms. It was done by Waff and Kang using the data obtained by Caceres, Carlos, and MacDonald. And then you obtain a continuum model. This continuum model will have several parameters. In fact, you know, it will have about 20 parameters, but not all of these are important for the flat bands. And in fact, if you project these models to the heavy fermion Hamiltonian, what you get is that the most important term, and the one that's the largest, that the strain introduces, is a splitting in this sector. This is the F fermion sector, right? And you can see the splitting, it just splits the F modes, and it splits them into, so you had 8 of them, it splits them into 4 plus 4, or 1 plus 1 per valley per spin, okay? And then you now have an extra energy scale in the problem, which is the strain, and now you can form many body states that you can fill or not fill these strained heavy fermions. Now, relaxation can also be introduced in this way, and relaxation, which breaks the particle hole symmetry of the Bister-McDonald model, is actually in this basis just a chemical potential of the heavy and light electrons that is different. If the chemical potentials are the same, the band structure will look like the Bister-McDonald band structure, exactly particle hole symmetric. If the chemical potentials are different, it will look like these generalized Bister-McDonald models that have this hump here in the flat bands and are not particle hole symmetric. You can repeat the formalism of you know, interacting symmetry broken states, non-symmetry broken states, etc. I don't have time to go through it, but basically what you get is the same results for the symmetry broken states that were obtained in the paper by Yves Kwan, Bultnix, Steve Simon, and Isid Parameswaran, which are these IKS states, and you find no gap at mu equals 0, no gap at mu equals -1, gap at mu equals -2, etc. You can see some Dirac nodes here, so no gap but Dirac nodes, etc. And these states would have the R3 pattern seen in the experiments. Now, the last thing, and I think, Eva, I hope you gave me permission to show this. I remember you did at some point, but there's, from Eva Andre's group, there's measurement of the entropy in these systems. And in this entropy, you can see two plateaus. Okay, and in these two plateaus, these are stray samples, as most of them are. In these two plateaus, you can see how well the entropy matches with that of, choose number of fermions, 8 choose number of fermions, or 4 choose number of fermions. There's two energy scales, that of strain and that of Hubbard-U. Now, ideally, this plateau at large T should stretch much longer because the Hubbard-U is much larger than 30 Kelvin, but you can do a calculation where you find that the phonons take over, well, back of the envelope, take over at this temperature. So we want to basically, identify this plateau as the strain number of fermions choose 4 choose number of heavy fermions, this as 8 choose number of fermions. This is how they look at different fillings. These things where the state goes down, where there's a mismatch at 2, might be because of ordering. These states are spin singlets at 2, so they should have 0 entropy if it orders. But in some symmetric state, which certainly happens at 20 Kelvin, etc., you should get plateaus that are equal to the entropy of the spins of the local moments. And indeed, you can see how good the match is until what we claim is that the phonons take over, but this requires more calculations. So I think with this, I thank you for your attention. Oh no, there was one last thing that I wanted to show you. So the other thing is I wanted to do a sort of a advertisement for another platform. That this is kind of a funny story because I thought along with my theorist and experimental friends, but at least I thought we would be the first ones to do this. But of course, Allan, we found out was doing it at the same time. So now there's 2 papers that showed up at the same time. All of the previous twisting was twisting of the K point, but there's a new platform where you can twist the M point. And in these platforms where you can twist the M point, you actually get trivial bands. But these trivial bands have very interesting interacting physics. They're topologically trivial, which means that actually you can map them into TJ models, and they have nice interacting properties, even though topologically they're trivial. The symmetries are completely different, and I would say that even though I thought we would be the first to do it, Allan was obviously doing it at the same time. So thank you, Allan, for all your leadership in the field. Thanks.
Okay, this same speaker again. So we have like 6 minutes past, so now it's a COVID. So maybe let me just call very quick question. Any quick before we? No.
Yeah. Okay, Sean. So is the thing that you said about this heavy fermion formulation, is it something general that can be applied to other systems too? Because it seems that it's just a band inversion.
It's a very good point. So I think so. I mean, I think basically the reason why in the business of MacDonald model, everything, all the Berry curvature, Berry curvature is 0, but the non-abelian version of it happens around the gamma point, is because the gap is the smallest at the gamma point. So that's where you have, here, every time you have a band that's very far away, you're not going to have band mixing. You're going to have no Berry phases. So that part you can localize. So I would expect around band inversions. So every time you have a topological band that's not in the chiral limit, but graphene TBG is not in the chiral limit anyways, very far away from it. So every time you have band inversions, which is the way you get topology, I would expect that the interacting description should be amenable to this. I'm not sure if it will be, but I hope so.
Yeah, so maybe we can continue like that.
Yeah.
So maybe let me end the session again. So let's thank all the speakers again. Thanks.